Chemical Kinetics, Part 4, determining the units for the rate constant K, and also we're going to take a look at how the magnitude of K affects the reaction rate. So remember that the rate of a reaction is a change in the amount of chemical divided by the change in time, and that we can describe that amount of chemical as moles, molarity or molar concentration, and partial pressure. So the units of moles would just be moles, and then the units of rate would be mole per second. The units of molar concentration is just capital M, molar, or moles of solute per liter of solution. And then the units of rate would be molar per second. And partial pressure could be in atmospheres or kilopascals or torr. And then the units of rate would be atmosphere per second, kilopascal per second, or torr per second. And once again, a torr is a millimeter of mercury. And by the way, you don't have to use seconds for the unit of time. You could use any unit of time that you wanted. So what we can do to find the units for the rate constant K is write the differential rate law, rearrange the differential rate law to solve for K, then we plug in units and simplify the units. The units of K depend on the reaction order. So we'll have different units of K for zero order, first order, and second order reactions. Or more than that, right? Third order or fourth order reactions too. So let's take a look at a few examples. Here's the units of K for a zero order reaction. Remember that the rate law in a zero order reaction, the differential rate law, is that the rate is equal to K. So we rearrange that, we get that K is equal to the rate. And let's say that the rate is being measured in units of molarity per second. Well, that would be the unit of K. If rate was being measured in mole per second, that would be the unit of K. Or atmospheres per second, that would be the unit of K. Whatever the unit of rate is, that's the unit for K. That's a zero order reaction. Here's a first order reaction. To find the units of K, we write the differential rate law, solve for K, and we get rate over concentration of chemical A. Plug in the rate, molarity per second, and the concentration molarity. Now the molarity is going to cancel out, and we'll get inverse seconds, or seconds to the -1 power, as our units of K. Notice they were different there than zero order, and they're going to be different here too for second order. The units of K for a second order reaction, here's the differential rate law for a second order reaction. Rearrange it so that you have K by itself. Now when you do that, you get rate divided by concentration of A squared. Plug in the units for rate. We're going to use molarity per second here, and then concentration, molarity, and that has to be squared, and simplify. Notice that the molarity up here in the numerator and one of these molarities in the denominator cancels out, so we get 1 over molar seconds, or molar to the -1, seconds to the -1 as our unit. And if you have multiple reactants, you can have third order reactions or more. So let's say we have a reaction that's third order. Here would be an example of a differential rate law that's third order overall. Rearrange that and solve for K. And in this case, we get rate is divided by concentration of A and divided by concentration of B squared. Plug in units for rate, molarity per second. Units for chemical concentration of chemical A is molarity, and units for concentration of chemical B is molarity as well, but we have to square that one. Simplify this, and you get 1 over molar squared seconds, or molar to the -2 seconds to the -1 power. So you don't ever really memorize the units for K. You just figure it out by plugging in the units and simplifying. Now the magnitude of K has an effect on reactions. Typically when we have big values of K, so large K values that are, say, greater than or equal to 1 billion or 10 to the 9th power, would be very fast reactions. And then small values of K that are less than or equal to 10 would be very slow reactions. And remember that K is temperature dependent. So for most reactions, we see that if you get them hotter, particles are going to move faster, and we're going to get more collisions in a short amount of time, and reactions will progress faster.